Hello, my name is Dakota Hofforth, and I'm a third-year neuroscience student. This video will highlight my project from this past summer titled Sensorimotor Functional Connectivity and Proprioception in Children with Hemiparetic Cerebral Palsy. I'll start today off by introducing to you a perinatal stroke, which is a focal vascular brain injury occurring between the 20th week of gestation and the 28th day of postnatal life. Recent research suggests that this is a relatively common disease occurring in about 1 in 1100 live births. This condition is associated with motor disability and is the leading cause of hemiparetic cerebral palsy, characterized by lifelong motor weakness in one side of the body. The first of the two types of perinatal stroke I'll be talking about today is arterial ischemic stroke, which results from an obstruction in a brain artery restricting blood flow and causing cortical and subcortical damage. Conversely, periventricular venous infarction results from impaired blood flow in veins near the brain's ventricles, causing damage to periventricular white matter. In this case, the cortex can be spared, which has impacts on proprioception. Proprioception is our sense of limb movement and limb position. However, children with hemiparetic cerebral palsy are impaired in this sense. A common test of proprioception is to hold out your thumb in front of your body, to close your eyes, and then to try to grab that thumb with the other hand. Someone with HCP would likely struggle with this task. In my study, I used the KINARM robot to assess proprioception, which is a robotic exoskeleton where the child performs different two-dimensional arm movement tasks. I used resting state fMRI to quantify the communication or functional connectivity between different brain regions. What we see here is a seemingly random graph representing the BOLD response or blood oxygen level dependent response of the left motor cortex. When we compare it to a time-matched graph of the BOLD level of the right motor cortex, we can see that these two brain regions are in fact highly correlated. Using this concept, we can construct a sensorimotor network consisting of brain regions that work together to generate motor output. The six regions I used to construct a motor map for this study include the primary motor cortex, primary somatosensory cortex, supplementary motor area, thalamus, caudate nucleus, and putamen. Which brings me to my hypotheses, the first of which was that children with perinatal stroke will show lower interhemispheric functional connectivity between brain regions. Secondly, I hypothesized that stroke-affected children will also show lower connectivity in the lesioned hemisphere compared to the non-lesioned hemisphere. And lastly, that lower connectivity in children with perinatal stroke will be associated with proprioceptive deficits. Our stroke participants were recruited from the Alberta Perinatal Stroke Program and our healthy controls from a hospital recruitment program. All of our participants were aged 6 to 19. For my imaging analysis, I defined the lesioned hemisphere as the non-dominant hemisphere, and vice versa. Depicted in diagram C are my chosen regions of interest and their connections, depicted by lines connecting each node. This diagram is color matched to figures A and B. I looked at three different KINARM standard tasks, the first of which is position matching, where the robot moved the impaired arm of the child to one of 8 different locations, and the child was instructed to match the final position using their dominant hand. Secondly, kinesthesia, which is similar in design. However, the child is instructed to match the movement in real time and not just the final position of each movement. Finally, for visually guided reaching, which involved reaches to one of 4 peripheral targets that would illuminate in a random order. The final sample included 112 participants, 33 with arterial stroke, 36 with venous stroke, and 43 controls. What I found was that venous stroke showed lower interhemispheric connectivity compared to controls only in subcortical regions, including the putamen, caudate nucleus, and thalamus. Conversely, arterial stroke saw lower connectivity across all sensorimotor regions we analyzed, both cortical and subcortical, possibly due to the locality of their lesions. I also found that arterial stroke showed lower functional connectivity within the lesioned hemisphere compared to the non-lesioned hemisphere, for the connection between the primary motor cortex and the putamen, the thalamus, and the primary somatosensory cortex. For my proprioceptive analyses, I ran partial correlations covariating for age and found significant correlations for all 3 tasks. Firstly, in position matching, I found that caudate functional connectivity was linked to movement variability only in controls. In kinesthesia, I saw that the primary somatosensory cortex, putamen, and thalamus connectivity was correlated to reaction time and indications of movement efficiency, such as direction error, for both types of stroke. Lastly, in visually guided reaching, I found that subcortical connectivity tracked movement accuracy and efficiency primarily in arterial stroke, while it tracked max speed in venous stroke. Some implications of this study is that functional connectivity is altered in perinatal stroke, suggesting the reorganization of sensorimotor networks, and that functional connectivity relates directly to both proprioceptive and physiomotor function. These results suggest potential biomarkers and rehabilitation targets for personalized care, and that developmental plasticity leads to complex network changes that follow early brain injury, which has consequences for proprioceptive function. I'd like to thank you for listening and to extend a special thanks to Dr. Helen Carlson and the rest of the team at BCI for Kids for making this project possible. Thank you.